Hello, students. I hope all of you are doing fine. I'm sharing with you the lecture notes for choppers, which is Unit 3 of Power Electronics of our syllabus. So let's get started. So, the entire content of the unit is divided into small lectures. In this particular lecture, I will be discussing the introduction to the choppers, the step down chopper, its basic circuit, and the standard circuit of step down chopper, which is also known as type A chopper. And there are certain practice questions which I'll float at the end of this lecture. So, choppers are basically DC to DC converters, which means that the input DC voltage, which is a constant source voltage, can be converted into various levels of DC voltage. This output voltage can be higher in magnitude as compared to input voltage, or it can be lower than the input voltage. So basically, it is a static device, and we can manipulate the output and get various levels of DC voltage at the output. So it is a variable DC output voltage. There are various applications where we require different levels of DC voltages. Such applications include trolley cars, battery operated vehicles, traction motor control, control of large numbers of DC motors. They are also used as DC voltage regulators. So we'll start with type of choppers, and first of all we will discuss the circuit of the conceptual circuit of the step down chopper. So the idea behind chopper is that it is basically a switch that connects input to the output at the intermittent time. So for some time switch will be on, for some time switch will be off, as you can see here. So what will be the output voltage? When it is on, V, which is the input voltage applied here, will be connected to the load. Load in this case is a simple resistive load. So corresponding to this, the current at the output is V upon R. So if it is a periodic behavior, that means the switch is on for certain time and it is off for certain time, and we take average over a time period, it will be some level of DC voltage at the output, and similarly we have some level of DC current at the output. So basically, for your information, the most important parameter here is the switching frequency of the chopper, which is also defined as 1 upon T. T is the switching time, and there is a constant time for which the chopper is on, and there is a constant time for which the chopper is off. So let us analyze the values of output voltage, current and power for this circuit. So the DC output voltage, which is also the average value of output voltage waveform, is given by the maximum value V into the time period for which the waveform is on divided by the total time period. So we write T on upon the total time period, which is sum of T on and T off, as capital T, and we substitute T on upon T as the duty cycle. Since it is a simple resistive load circuit, we know that if we know the voltage, current can be derived as V upon R. So VDC we have already derived as V into D. So current is V into D upon R, where D is the duty cycle. Let us see what is the output RMS value voltage. The RMS value of output voltage is represented as VO here, and it can be derived using this formula, where for the time period where the waveform is on, that is 0 to t on, we put the value of voltage equal to V. We calculate it as the under root of t on upon t into V. So again, this comes out to be under root of d into V. Let us see what is the output power here. So if we note the RMS value of output voltage and RMS value of output current, which is the current will be equal to RMS value of output voltage upon R, and the power is equals to V naught square upon R, where V naught is equals to under root D into V, which comes out to be dV square upon R. So let us examine the working of the basic step down chopper with RL load. In case of RL load, E represents the back EMF, so loads become RL E load. Here the circuit is discussed because we need to understand what is the difference between the continuous current mode conduction and the discontinuous current mode conduction. In case of continuous current mode conduction, the current through the load, it rises from I minimum to maximum value, and during off time it falls from I maximum to I minimum value. In case of discontinuous current mode, this minimum value of current may reach 0 in between the on and off time. Whereas in continuous current mode, the consideration is given such that I minimum is always positive and never reaches 0. When the chopper is on, in that case, the current will be flowing through the inductor load RLE, and the freewheeling diode will be reverse biased. Whereas when the chopper is off, in that case, the current still flows and obeys the same direction, which is completed through freewheeling diode, and supply voltage is disconnected with the load when the chopper is off. The output voltage can be given in terms of this expression I naught R plus L di I naught upon dt plus E in this case. So there is some issue with this basic circuit configuration of buck converter, because this circuit can be used in some primary applications such as controlling the speed of DC motor. The circuit is not sufficient for the case when the objective is to produce a pure DC output. So in that case, we need to connect a low pass filter between the source and the load, so that the circuit is able to produce a nice DC output waveform. A low pass filter is designed using inductor and a capacitor, which we will see next, and it is known as a standard buck converter circuit, and it will be analyzed in detail in the further section. The standard circuit of buck converter, which is also known as step down converter, is discussed here. In the standard circuit, we have L and C, which becomes a low pass filter. The purpose of connecting inductor is to reduce the current ripple, while the value of capacitor in parallel with the load will help us reducing the voltage ripple. So when the switch is on, that means chopper is on, at that time Vs will provide a current through the inductor, and inductor will store energy. The voltage drop across inductor at this time can be given as Vs minus V0. The diode is reverse biased, and the circuit configuration is as shown in figure 3b. When the switch is off, it disconnects the input supply voltage, and now the stored energy through the inductor is provided to the load. Since Vs becomes 0, so the voltage drop across the inductor in this case is minus V naught. Diode is forward biased. The waveform for inductor is as shown in the first figure. Here during on time, when chopper is on, the voltage is Vs minus V naught, and during off time the voltage is minus V naught. The current through the inductor, it flows from I minimum to maximum value during the chopper on time, and it flows from I maximum, it drops down from I maximum to I minimum when the chopper is off. The capacitor current follows the same wave shape as the inductor current, because IL can be given as the sum of IC plus IR. The average value of inductor current is same as the average value of load, so we represent it as IR. The average value of capacitor is 0 because IC is equals to IL minus IR. So if we subtract IR from the inductor current, the capacitor current average value becomes 0. Also, we know that T on upon T is the duty cycle represented as small d. So we can use T on equal to D into T. T is the switching time of the chopper, and T off is equals to 1 minus D into T. So let us carry out the detailed analysis of buck converter. So first condition is when the switch is closed. So this is the T on time. During this, the supply voltage is connected to the inductor, capacitor and the load. So the inductor voltage drop is given by Vs minus V naught, which can further be written in terms of inductor current IL as L DIL upon dt. So Vs upon V naught upon L will be equal to DIL upon dt. So how can we further find out this DIL upon dt? It is change in IL upon change in T. So change in T is nothing but the time for which the switch is on, which is T on time. This T on time can be written in terms of duty cycle as D into T. So equating these two, delta IL upon dt is equals to Vs minus V naught upon L. I can find out delta IL closed equal to Vs minus V naught upon L into dt. When the switch is open, the circuit becomes like this. Now, since the current will still flow through the inductor, the path will be provided through the diode, and Vs becomes 0. So the inductor voltage drop is equal to minus V naught. So VL is equals to minus V naught, which can further be written as L DIL upon dt. So to find out DIL upon dt, we know that dt is equal to delta t, and this is the time for which the switch is off. And the off time can be written in terms of duty cycle as 1 minus d into t. So equating these two, I can find out delta IL open equal to minus V naught upon L 1 minus d into t. So we have these waveforms for inductor voltage, inductor current and capacitor current. So in case of inductor current, we know that the current increases from some minimum value to some maximum value. This minimum and maximum value of the current can be determined in terms of delta IL, and this is the reason why we have calculated delta IL in this case. So I can write down I max and I min as IL plus delta IL upon 2 and IL minus delta IL upon 2. So let us further analyze the circuit in its steady state condition. The steady state operation says that the inductor current at the end of the switching cycle should be same as that of the beginning. Therefore, the net change in inductor current over one period is 0. So the change in inductor current during off time and during on time, the sum is equal to 0. We can put the value of these two And we can solve this expression for the value of V naught, which comes out to be V naught is equals to Vs into D, and the duty cycle D is always less than or equal to 1. Therefore, the output voltage in case of buck converter is always less than or equal to the supply voltage. So this is one of the important expressions. Further, the average inductor current should be same as average value of the load current, because the average capacitor current is 0. Therefore, we can equate the average value of inductor current to the average value of the load, which is a resistor, and resistor current can be written as V naught upon R. So if we use an expression of I maximum, which is equal to the average value of inductor current plus delta IL upon 2, I can further substitute the value of delta IL. Delta IL you can use either for delta IL closed or delta IL open. I am using it as delta IL closed here. So if I put the value of delta IL closed, I max is determined and it is shown here. Where further 1 upon T can be written as the switching frequency. So we rearrange the expression and Imax is calculated. Similarly, Imin can be calculated as IL minus delta IL upon 2. So again, substituting the values, I can determine the value of Imin. So further we find out the design equation of L and C. To find out the value of inductor, we determine the boundary condition. The boundary condition is in terms of I minimum, because I minimum is 0 at the boundary, which is the condition between the continuous and discontinuous current mode. Because for the continuous current mode, I min can only be positive. So we use the condition I min is equals to 0, and we use the expression of I minimum, which we have already calculated. Putting it equal to 0, we find out the value of inductor L equal to 1 minus D into R upon 2 into F, and this is the minimum value of inductor required for the continuous current mode conduction, which means that you can select, while designing the circuit, you can select the value of inductor which is higher than the calculated value L minimum. For C, we can use the expression Q is equals to C into V naught, or change in Q is equals to C into change in V naught, which can further be written as delta V naught equal to delta Q upon C. So how do we determine it further? Delta Q is nothing but the area under this curve. Delta Q can therefore be written as 1 upon 2 into T by 2 into delta IL upon 2. So we can also write down delta V naught, which is delta Q upon C, and delta IL we have already calculated. So substituting the value of delta IL, we find out delta V in terms of D, the value of L and C, and the switching frequency F. The ratio delta V upon V naught upon V is known as the percentage ripple at the output. So delta V naught is basically the change in the output voltage. So C can be written in terms of what percentage value of ripple is acceptable at the output, the switching frequency at which we can design the circuit, the duty cycle, and the minimum value of L. So C can be determined using this formula. So as we conclude the design consideration of buck converter, the design which we have discussed is the continuous current mode operation. Switching frequency is one of the important parameters, because the switching frequency, if it is high, a low value of inductor and capacitor would be required in the circuit. Particularly in case of inductor, because inductor is a bulky component, so usually a high value of switching frequency is opted, but as switching frequency increases, the power loss in the circuit also increases. So some trade-off is required to select the optimal value of switching frequency, and usually a frequency greater than 20 kilohertz is selected to avoid audio noise. It can extend up to hundreds of kilohertz and even in a megahertz range. So using all the expressions which we have discussed, you can practice some questions which are given in the next slide. Thank you.